Hello, welcome to another module in this massive open online course. So, we are looking at the properties of the Laplace transform. Let us continue our discussion. Okay. So, what we want to look at now is another interesting aspect of the Laplace transform is its relation to the convolution between two signals. So, we want to look at the convolution aspect or the convolution property of Laplace transform. So, let us say I have two signals x1t, which is x1s Laplace transform with ROC equals R1, and x2t with Laplace transform x2s and ROC equals R2. Then if we have the convolution x1 t convolved with x2t, I consider the convolution x1t convolved with x2t, I want to find out what is the Laplace transform of x1t convolved with x2t. Well, you can see x1t convolved with x2t can be expressed as integral minus infinity to infinity x1t convolved with x2 or x1 tau times x2 t minus tau d tau, and we take the Laplace transform. So, this is the convolution, the inside integral, and you take the Laplace transform of this e raised to minus st. So, this is the convolution, this is the inner integral, and basically outer integral is taking the Laplace transform of the convolution. Okay. And now this you can simplify this by modifying the order of integration as follows. I can make this as integral minus infinity to infinity x1 tau times d tau into integral minus infinity to infinity x2 t minus tau e raised to minus s t dt. And now what I can do here is basically I can write this as integral minus infinity to infinity x1 tau d tau integral minus infinity to infinity x1 t minus tau e raised to minus s t minus tau d tau. So, I can changing e raised to minus s t minus tau, which means I will there is a factor of e raised to minus s tau which I am writing outside. So, I am multiplying by e raised to minus s tau into e raised to plus s tau. Okay. And now you can see if I look at this integral, if I set t minus tau equals t tilde, then I will have dt or minus d tau, t minus tau equals by the way, this integral is with respect to t. So, this is t t. So, I will have dt equals d tilde, and I can further write this integral as e integral minus infinity to infinity x1 tau e raised to minus s tau d tau into integral minus infinity to infinity x1 t tilde e raised to minus s t tilde dt tilde, and you can see this is basically your x1s. So, this you can see is basically your x1s, and this which does not depend on t tilde is x2s. So, what you have is, I am sorry, this is basically your let me just write it, this is x1 tau, so this is x2, this is x2 tau, so this is x2 t minus tau, so again this is x2 of t tilde, and so this is basically your x2 of s, and this is in fact your x1 of s. So, just write one more step. So, this is x2 of s which comes out of the integral, and what you are left with is x2 of s integral minus infinity to infinity and this you can see is x1 of s. So, what you have is x1 of s times x2 of s. So, basically the result that we have is that the convolution of two signals, if we convolve x1t with x2t, the Laplace transform is given by the product of the Laplace transforms, that is x1s times x2s, and this is a very interesting result. So, x1t convolved with x2t has Laplace transform x1s times x2s. So, convolution in time is equivalent to taking the product in the transform domain, that is the Laplace domain. So, convolution in time the product in Laplace transform domain, or basically the S domain, and this is an important product. This is an important property. What it does, it helps easily evaluate. So, this property helps easily evaluate the convolution between two signals. This property helps easily evaluate the convolutions of two signals, because rather than evaluating a convolution, which is slightly difficult to evaluate typically because it involves the integral, if one has knowledge of the Laplace transforms of the two signals, then the Laplace transform of the convolution can be rather readily evaluated by the multiplication of the Laplace transforms of these two signals. So, that is important. So, it is a very convenient tool. So, the transform domain representation gives a very convenient tool to evaluate the convolution between two signals, and hence as a result of that, naturally it's easier to look at the output of an LTI system given an input signal, because the output is nothing but the convolution between the input signal and the impulse response of the LTI system. So, as a result, so the properties and behavior, so which implies this, that it is a convenient tool to analyze the output or behavior of LTI systems, that is linear time invariant, uses a convenient tool to analyze the output or behavior of LTI systems. Therefore, the Laplace transform is a very convenient tool in both signal processing, communications, several areas such as control systems, correct, instrumentation, etc., where one needs to study the behavior of system, analyze the behavior of system, examine the behavior or the output of a given system for different input signals, and also analyze the impact of the system for give different signals, okay, characterize the interaction between various signals and systems, okay, all right. So, let us now move on to another topic in the Laplace transform, which is that of the poles and zeros the poles and zeros. Now consider xs to be a rational function of s. We consider the Laplace transform to be a rational which implies xs is the form of numerator polynomial divided by denominator polynomial. So, this is going to be of the form a naught s minus z1 s minus z2 s minus z m, or let us write it this way, this is of the form a naught s to the power of m plus a1 s to the power of m minus 1 plus am divided by b naught s to the power of n plus b1 s to the power of n minus 1 plus bn. Okay. So, this is of the form numerator polynomial divided by denominator polynomial. Numerator polynomial divided by denominator polynomial, and therefore, this can be written as a naught over b naught into s minus z1 s minus z2 s minus zm divided by s minus p1 s minus p2 s minus pn, okay, where these roots of the numerator polynomial, that is zk for 1 less than or equal to k less than or equal to m, these are known as the zeros. Okay, these are known as the zeros of the transform, that is the roots of the numerator polynomial in S. These are known as the zeros of the transfer function, and the roots of the denominator polynomial in S are known as the poles of the transfer function. So, zk or the zeros of the transfer function, pk are the poles of the transfer function, okay, and this is known as a proper rational function. Proper rational function if m is strict. So, if m is strictly less than n, then this is known as a proper rational function. If m is greater than or equal to n, this implies that is the numerator degree of the numerator polynomial. So, m, remember m equals degree of numerator polynomial, and n is basically degree of denominator polynomial. Degree of numerator, and if m is greater than or equal to n, m is greater or equal to m, this implies an improper rational function. Okay. So, if the numerator polynomial degree is less than the degree of the denominator polynomial, it is a proper rational function. On the other hand, otherwise, that is degree of numerator polynomial is greater than or equal to that of the denominator polynomial, it is an improper rational function. Okay. All right. And now, one thing to keep in mind is that poles cannot lie, the poles of x of s, poles of the transfer function cannot lie in ROC, since the excess is undefined at the poles, or since excess evaluates to infinity at the poles, since excess equals infinity at poles. So, poles cannot lie in the ROC, poles of excess cannot. So, ROC, the region of convergence, cannot include poles of the transfer function excess. Okay. Let us take an example to understand this better. Okay. So, I have excess equals 4s plus 3 divided by 2s square plus 6s plus 4 equals 4 into s plus 3 by 4 divided by 2 into s plus 2 into s plus 1. Okay. So, this is equal to, basically you can write this as twice of s plus 3 over 4 divided by s plus 2 into s plus 1, and now you can see here that the zeros, z1 equals minus 3 by 4, this is a 0, and p1 equals minus 2, p2 equals minus 1, these are the poles, and ROC cannot include these poles, the ROC cannot include minus 2 or minus 1. ROC cannot include poles that are equal to minus 1. So, the poles are minus 1 and minus 2 and minus 1, the ROC cannot include poles, and also you can see this is a, now m here, degree of numerator polynomial, m equals 1, n equals 2. So, you have m less than m, implies this is a proper rational function. This is a proper rational function. Okay. So, what we have just solved or just considered as an example is a proper rational function. The Laplace transform is a proper rational function. Okay. All right. Let us look at some of the properties of the ROC. Now, the properties of ROC, the first property, as we already seen, ROC does not contain poles. ROC does not contain poles for a finite duration signal. For a finite duration signal, that is xt equal to 0 for t greater than or t less than t1 or t greater than t2. okay, implies that signal is non-zero only for t1 less than equal to, that is non-zero only in the interval t1 to t2. Okay, it is a finite duration signal. For such signals, the ROC is typically the entire S plane. Okay, so this is a finite duration signal, implies xt equals not equal to 0 only for t1 less than equal to t less than equal to 2, ROC equals the entire S plane. ROC equals entire S plane. Now, for a right-handed signal, correct? Now, for a right-handed signal, this implies that xt equal to 0 for all t less than some t1 which is less than infinity, that is this right handed signal is 0 it is some signal that looks like this. So, at t1 for all t less than t1 this is 0 and non-zero only for t greater than t1, that is it exists only on the right hand side, it is non-zero only on the right hand side. For this kind of a signal, for a right handed signal, the ROC is of the form the real part of S is greater than sigma max, where sigma max equals the maximum of the real part of the poles of excess of the Laplace transform, maximum of real part of poles of excess. And this ROC, remember the ROC is real part of x s greater than sigma max this implies that the ROC is to the right half, ROC equals the half plane to right of the vertical line given by real part of S equals sigma max. So, this is to the right of the line given by real part of S equals sigma max, implies this is to the right of all the, since it is greater than the real parts of all the poles. So, sigma max is the maximum of the real part of all the poles, implies that the ROC is to the right of all poles of excess. And the ROC will look something like this, that is you have your S plane, okay, and you have your sigma max, alright. So, this is let us say your sigma max, then the ROC will be sigma max, okay. ROC will be real part of S greater than sigma max, and remember all the other poles can only be on the See, remember the ROC cannot contain any poles, correct? The ROC cannot contain any poles. So, all other poles are to the left, are in the so the ROC is basically to the right of all the poles. So, ROC is on the left of this line given by real part of S. So, this is the line which is real part of S equals sigma max. And of course, this line itself is not included in the ROC. So, let us take an example, let us look at a simple example to understand this. Example, consider xt equals e raised to minus 2t ut plus e raised to minus 3t ut. Okay. This is a right handed signal, you can clearly see that, correct, exists only for t greater than 0. Non-zero only for t greater than or equal to 0, correct. It is a right handed signal, and if you look at the Laplace transform of this, that will be xs equals, well, that will be xs equals 1 over s plus 2, we have seen that, plus 1 over s plus 3. The poles are minus 2, s equal to minus 2, comma s equals minus 3, and the ROC, now the maximum, remember, look at this, minus 2 minus 3, this is sigma max is minus 2, maximum of the real part, sigma max is minus 2, and therefore the ROC is real part of S greater than minus 2, okay. And so this is the ROC, and the ROC looks like this. If you plot this, this is your sigma, this is your S plane, this is your sigma, this is j omega axis, y axis is the j omega axis, this is the line sigma max, S equals, this is the line as real part of S equals sigma max, that is minus 2, okay. And remember, somewhere here you have minus 3, and the ROC is this part, that is real part of S greater than minus 2. So, all the other poles lie on the left of this line, real part of S equal to sigma max. So, ROC is to the right of all poles. So, this is real part of S greater than minus 2, and this is your ROC for the right handed signal, okay. So, this is the ROC for the right handed signal, and this quantity here, this is equal to sigma max, and this is the line real part of S equals sigma max, and ROC is the region to the right of this line, real part of S equals sigma max, and in fact it does not include this line, real part of S equal to sigma max. That is something important to remember, okay. Now, let us look at what about a left handed signal. For a left handed signal, everything becomes the opposite of what we said so far for a right handed signal. So, for xt equal to 0 for, well, t greater than t2 greater than minus infinity, that is t2 cannot be minus infinity, okay. And for this, that is this is termed as a left handed signal. This is termed as a left handed signal, and ROC of this is of the form real part of S less than sigma min, where sigma min is the minimum of the real part of the poles of XS. That is what we said, it is opposite of the right handed signal. Sigma min equals minimum of real part of poles of X of S, okay, and is a minimum of the real part of the poles of X of S, okay, and implies the ROC equals region of S plane to left of line real part of S equals sigma min. So, ROC is the region to the left of this line, in fact not including this line, real part of S equal to sigma min, and this also implies that is it is to the left of all poles of X of S, implies ROC is left of all poles of X of S. Okay. And a simple way to look at it, again once again simple illustration, S plane sigma j omega let us just to not make it similar, let us say this point is your sigma min, this line is real part of S equal to sigma min, then the ROC will be this real part of S less than, the ROC will be real part of S less than sigma min, and this is your ROC. ROC equals real part of S equal less than sigma min. Okay. Let us look at a simple example to understand this. Consider the signal xt equals minus e raised to 2t u minus t minus e raised to 3t u of minus t. Now, you can see that this signal, this is a left handed signal, this is a left handed signal, and this is non-zero only for non-zero only for t less than or equal to 0. Okay. And the Laplace transform of this signal is given as, you can find the Laplace transform, you can easily check that the Laplace transform is 1 over S minus 2 plus 1 over S minus 3, and from this you can see that the poles of this system equals 2, 3, and clearly you can see sigma min equals 2, and therefore, the ROC of this left handed signal is of the form real part of S less than 2, real part of less than sigma min, which is 2, and therefore, this is the ROC of the left handed signal. All right. And ROC plot again is given similarly. So, ROC is plot is given similarly. This is sigma, this is j omega axis, and this is your pole which is 2, and of course, this is the pole which is 3, this is the line real part of S equals 2, that is equals sigma min, and ROC is to the left of this, ROC is to the left of this, that is real part of S less than 2. And you can see all poles have to lie only to the right, that is ROC has to lie to the left of all poles. Okay, ROC has to lie to the left of all the poles of XS. Alright, so we will stop this module here and continue with other aspects in the subsequent modules. Thank you very much.